All right, so one last thing of inference for slope, chapter 12. But real quick, I have the notes here just to highlight when you're using the calculator. If all you want to do is turn a chi-square into a p-value, use chi-square CDF. Mostly I wanted to say this, right? So Goff tests, you need to have two lists, L1, L2, and then you run the Goff test, and here's what you type in. For the other two tests for two-way tables, this is either homogeneity or association independence, you have to have your first step, put everything into matrix A, which is second x negative 1, matrix edit A, dimensions, blah, blah, blah. And then when you run it, observed A, expected B. That's the one where this stores your expected as B. You don't have to do anything to matrix B. It will do that on its own. Okay, so you have that page of notes in the middle of your notes. Now we're down here. 12.1a, our last inference. Inference for linear regression. So this will be way back, review of chapter 3 a little bit. So if we find a least squared regression line, right, that's what that's called. If we actually have all the data, which remember is called a census, we call this the population regression line, or we could call it the true regression line. It has the equation, what? Well, it used to be y a plus bx. Well, for the true one, we're going to call it y, but instead of a, we'll do alpha. Instead of b, we'll do beta x. And then if we, in a more realistic, we just take a sample of the whole population. This is what we actually did back in chapter 3 often. Then we have this, we call this a sample regression line, and it has the equation y hat equals a plus bx. And so, what are the three parameters that we have in a regression model? What statistics do we use to estimate them? So we have what we're normally doing. This is the first one's the only one we actually are going to work with. But you could do these other ones. But you have beta, the true population slope, and you're going to try to estimate little b, the sample slope. Or, well, I kind of said that backwards. You're going to estimate it with b. Then you have alpha, the true y-intercept, and you could then have a sample y-intercept that we just call a. And then another one, though, that we always measure with these could be the true sigma, which with these, if you remember, that's called the standard deviation of the residuals, which is interpretation. Typically, when using this line to predict this, we're off by this much. And then, so we would then call that, we were calling in chapter 3 just little s, and little s then is trying to estimate that big S. So now, just like the other chapters, all of our inference begins with a sampling distribution. So what would happen if you did a whole bunch of every possible sample of 20 points out of this population? What would that look like? And again, we're only really going to be looking at slopes. What would happen to all the slopes? Well, on average, they will be centered at the real slope. And on average, they will have a standard deviation of blah, blah, blah. Well, so in order to do inference in this chapter, we won't go into a lot of detail on the rest of that. But so in order to do inference, we still have to check certain conditions. You have to make sure the sampling distribution isn't biased, or else we're not going to be centered on the right slope if we only got points that don't really represent the population. And we're going to have to do something with like normal curves or something, so we can use like z-scores or t-scores or who knows. I guess we'll find out later. And so it's still the basic conditions. It is very doubtful that you will have to do a four-step like panic or phantom problem where you actually have to check all of these on the AP exam. We will still practice this. We will still test on this if we get to do tests again and so on. But you don't have to probably list all these out. They might ask questions in the multiple choice, things like that, so we're going to go ahead and cover them. It's still basically random, normal, independent, but now you can see we had to add some. We still have the I, the N, and the R, but we want to spell the whole word liner, which is not too bad. A couple of them are a little weird, but it's pretty easy to practice. So here we go. The L of liner just stands for linear. So basically for every x, the average of all the y's at that x is on the true regression line. So this would be like if you had the, way back we did, what did we do? Cars sales? Maybe that was last year. But anyway, let's pretend we have a bunch of data on how many miles you have on your truck and how much it would sell for. So that would mean that on average, a truck with 20,000 miles, if you took all the trucks with 20,000 miles and averaged their price, that average would be right on the line of some sort. So all you have to do for this is just say the data is approximately linear. And so to check, we say the scatter plot is roughly linear, which they usually give you in these problems. You don't have to graph those by hand almost ever. Or remember, it's the same as before. The residual plot has no clear pattern. And technically, they might add the residual center on 0 at every x, meaning there's some above and some below, and so they average right on the line. That one's usually pretty easy to say the data is approximately linear, not normal. I still for independent, which is always the same. So if it was random, then I check the 10% condition and so on. The N is still normal, but here it's really weird. For every x, the y variable is supposed to be approximately normal. This one is almost impossible to actually check, which is, because we normally don't have, really to do this, your sample has to be like thousands. But technically what you're supposed to do is you somehow look at all the residuals, but not just in a residual plot, but a plot of all the residuals, which is usually either a stem plot, histogram, or probability plot of the residuals, and check if it's skewed, or if it looks approximately normal. You'll just have to see this when we do an example, or look up an example in the book. But that's technically a condition that needs to be checked. However, that one often is not really checked, and so is this next one. So the E stands for equaled standard deviations, or equal spread. The standard deviation of y is the same for all values of x. I'm looking at this and I legit don't know what that's supposed to be. Oh, s sub y. The standard deviation of y, s sub y, is actually, I'm not sure what that blank is supposed to be. Sorry, guys. A little thing I do with this is if you're looking at the residual plot, the next line to check on the residual plot, the vertical spread of the residuals should be about the same, which basically you're just trying to say no, like Christmas tree. And let me sketch that. So it shouldn't, the residual plot shouldn't look like this. Every x should have about the same spread. Again, this one is hard to actually check. And so I'm saying all these, but this is not as vital as your standard random normal independent. However, it could come up, and we are going to practice it. And then lastly is the same as always, random. We just put them in a different order so it's spelled liner. But the data needs to be random or a randomized experiment. And again, for that, like always, you pretty much just quote the problem. Now, when checking conditions, you can count on having all those needed graphs. And you'll still need to know each condition in words, though, for multiple choice questions. Okay, so all that stuff was about the checking conditions so we can do inference. And now instead of just phantom, like chapter 11, we can also do panic. And we're going to be doing that all for the true slope. And so if we're going to do something with the true slope, we're going to need to know the true standard deviation of the slope. And so on the formula sheet, this is just right below the other ones. We have that the if I have little slope b, then the average of all of the sample b's should be the real beta, and the standard deviation of all the b's should be the real standard deviation of the standard deviation x times the square root of n, where the standard deviation of x, just this bottom number, is this whole formula. Or when instead of using this, we use s, we call it the standard error instead of standard deviation, and then we replace it here where s is this formula. This is the standard deviation of all the y's, basically, and this is the standard deviation of all the x's, and this is really complicated, but thankfully, we will never have to use it. Q, next thing. Because whenever they give us these problems, they always, remember this thing? They always give us these, data, these little chart thingies. So maybe we should review all of this real quick, right? Do you remember this? So we're going to do this on the notes. So the constant is anything to do with y. The points per game would be something to do with x, or the slope. If I do a plus bx, then a is, there's nothing there. But x, that would be like bx, that'd be my slope. And so the coefficient of points per game, that's the slope. The coefficient of the constant, that would be my y-intercept. I'm guessing this is like the number of wins or something like that. Well, the next column is the standard error of the coefficient. We ignored this back in chapter 3, but this bottom number, this 0.05205, that is the standard error of the points per game. Well, that's my slope. So my standard error of my slope, if I were to, rather than using that big complicated formula, is just right here. Now these other numbers, real quick, now you're going to have to remember all these cookie cutters, tomorrow's notes, and one of the examples in the homework will have that. So this S, this is the standard error or standard deviation of the residuals. This means when I'm predicting whatever I'm predicting based on points per game, I'm typically off by 1.23. And then the R square and the R square adjusted we always ignored. The R square is just how good my fit is. The closer to 100%, the better. It's also literally R squared, so if I square root of that, I get R. Now this T and P are all these are going to be related to significance tests. This P value is 0. It means there's the significance test of whatever I'd be testing here would be significant, but we'll get to that. So what is the standard error of the slope? More importantly, how do you interpret it? So the standard error of the slope is from the formula sheet. I guess we could write it down. It's simply the well, here. If we knew the real sigma, it would be that, but since we don't, we say the standard error of the slope, with an s instead of a sigma, is the standard error of all the y's over the standard error of all the x's, and then it's n minus 1 because of reasons I honestly don't remember right now why it's not still an n. But anyway, we don't have to do that because it's right here. Standard error of the slope is that number right there. So how do you interpret it? Well, in general, standard error, standard deviation is always something typically varies by this much. So what is typically varying? The standard error of the slope means the slope of the sample regression line typically varies from the slope of the true regression line or population regression line by blah blah blah, the standard error. All right, here's a nifty little experiment of dropping helicopters and seeing what they do. Measured flight times, and so the higher we dropped it from, the longer it was in flight. Well, duh. But is it linear? Is it like once you hit a certain point, does it all of a sudden catch more air and hit? I don't know. So anyway, are the conditions for performing inference met? And then there's going to be a bunch of other questions about cookie cutters. So, okay. So are the conditions for inference met? I scrolled up a little bit because we need to start checking conditions. So now we're just going to trust our new thing, liner. Okay, so actually real quick before I do that, this is the scatter plot. Note that we only dropped them from 5 different heights, 14 helicopters to each. So that's why all the dots are on top of each other. So that's the scatter plot. This is called the residual plot because you have residuals and it's centered at 0. It means some helicopters were above. They flew longer than we expected and some are below. This is the residuals. This is the residuals. This is called z-scores. This is called a normal probability plot. And this is called a box plot, histogram, histogram. Box plot's the like boxing whisker plot. So this is a histogram of the residuals. Okay, so all of those are helping us to check liner. So linear, sure, the scatter plot or no pattern in the residuals. I mean, I don't know, there's almost a pattern here, but we would just say the scatter plot is approximately linear. Check. I, independent. Well, it was an experiment, and I think it's safe to assume every helicopter was independent of the others. Otherwise, you're checking 10% condition, but this was a, what did I just say, an experiment. Normal, well, yeah, let's see, any of those. The normal probability plot of the residuals is roughly linear. Or the standard, or the histogram of the residuals is approximately normal. Either of those. Equal standard deviations, E, liner. So that's the residual plot. I mean, the one at 300 is spread clearly more than the others. There's no clear pattern that the spread is changing. So, yeah, I don't know. I mean, not really, because one of them's clearly more spread than the others. And the whole point is they're supposed to be equal. So, I don't know. Random, sure, they were randomly assigned into their groups. All right, now it's going to ask for a bunch of other things. What is the estimate for beta 0? What is beta 0? That's actually just the y-intercept. It just is wording it weird. And then to practice, we're going to interpret that. So I'm actually going to move back up here. So this is letter A. So the y-intercept, that's the coefficient of the constant. And we would interpret it by saying when the x is 0, the y is this much. So when a helicopter is dropped from 0 centimeters, we would predict, remember to have the word predict, that it would take negative 0.03761 seconds to land. Maybe a side note, this is nonsensical in the context. Letter B, what is the estimate for beta 1? That's just, what is the estimate for beta? That would be the true slope. Oh, well, just be my slope. So 0.005724. And we would say, for each centimeter we increase the drop height, we would expect the flight time to increase by 0.0057 seconds. Make sure you have the word predict. What is the estimate for standard deviation, sigma? Well, we would estimate sigma to be S, 0.168. And that is the actual flight times typically vary by 0.168 seconds from the times predicted by the least squared regression line, or something to that effect. So these are all our old cookie cutters. I want you to practice these in the bookwork. And then lastly, give the standard error of the slope. That's now this new number right here, 0.000218, 2018. What a good year. And interpret that. Okay, when we are, what? The slope of the sample, when we're getting a bunch of slopes, the slope of the sample regression line typically varies from the true slope by 0.000 2018. Okay, so your book work for tomorrow is just, or for by midnight, is just 2 problems from this new section. I believe at least one of them is liner. I think it's the same problem but 2 parts kind of thing, kind of like what we just did. And then way back, this is chapter 3. I would like you to do 3.4. This is in the review section. It's on page 199, where you're just practicing all these old cookie cutter ones. And then we're going to practice them again because it's been a while, and we're going to need them all again here for chapter 12. So have fun.